Welcome to Gas Videos 2. In the last one we discussed different types of pressure, or at least the conversion between a few different types of pressure. In chemistry, a lot of times what we're doing is we'll produce gases and then want to measure the pressure that the gas exerts. One of the devices that we use in science to measure this is called a manometer. And if you look on the right-hand side of this screen, you'll notice it says gas, and then it has this tube, and it's got a kind of a catch area. And what's inside this tube is actually mercury. And if the height of the mercury on both sides is equal, that means the pressure outside, this, by the way, is an open-ended manometer. In other words, the pressure from the atmosphere out here is actually pressing down. It's driving down this tube. If the height of this mercury on this side is equal to the height of the mercury on this side, then the pressure outside is equal to the pressure inside. So let's say, for example, the pressure up here happens to be, let's just say it's 760, so it's atmospheric pressure. And so what we're doing is we're saying, you know what, the pressure outside the column and the pressure inside, or the pressure outside the column, is 760 millimeters of mercury. Now, the problem is the mercury is getting pushed up towards that 760, so it has to overcome 760. And so what we're looking at is, by looking at this gas being pressed up, again, if we look at where it's being pressed, down here, the gas is pressing down on this, driving the mercury up. So here's the level of the mercury inside the bulb, and the level of the mercury outside the bulb is up here. So we have a difference of 18.8 millimeters. So the pressure inside the chamber, inside with the gases over here, is higher because it's pushing than the outside. And so if we wanted to calculate how much higher, what we do is we take our 760 millimeters of mercury, because that's what's pushing down, plus how far our column has been pushed up, which is 18.8 millimeters of mercury. So by adding those two things together, we should get, what do we have, 778.8 millimeters of mercury. Now, that's the pressure of the gas right here pressing down on this column of mercury and driving it up. Now, something to remember as you start to play around with this is, if we look at an open-ended manometer, there's two types of manometers, and one of them is open-ended and the other one's closed. The open-ended manometer, the way you figure out the pressure of the gas that's in the chamber, is you take the pressure of the atmosphere, well, we're pressing down with 760 millimeters of mercury, plus the height of the mercury. In other words, this little segment, let me see if I can circle it, this little segment here, the height of the mercury, is equal to the total pressure of the gas inside the chamber. So when we're starting to calculate, do manometer problems, what we're looking for is the pressure that the gas is exerting. Now, like the barometer in the last problem, if this manometer happened to be closed end, so basically what we're going to do is shut off, cap the other end. Now, if both sides of the mercury are equal, then there's no pressure either side. This will drive down. If this thing is capped, if it doesn't go anywhere, in other words, this is plugged, and that mercury is pulling down, what we're seeing is the total pressure of the mercury on a closed-ended manometer, which would be easy, is 18.8. It is the height of the mercury. So if this is a closed-ended manometer, the pressure is the height of the mercury. So in this case, 18.8 millimeters of mercury. All right. So moving on with pressure, we need to start comparing some things. So here's my closed-ended and open-ended. So notice in this particular case, they have a calculation. They're doing kilopascals, so they converted my 655 millimeter drop. Notice that the mercury is lower on this side. than it is on this side. So the gas is less pressure than the atmosphere. They did a little conversion to figure out how many kilopascals it is. In this particular problem, here's a closed-in manometer, and what we're seeing is the push up of the mercury. So it jumps up 105 millimeters of mercury. And so we can see that in a closed-ended, that is the pressure, 105 millimeters of mercury. In a open-ended, we would actually subtract the 650 from 760 millimeters mercury. So it would be 760 minus, in this case, 655, okay, to get our pressure. All right, so that kind of ends our section just on pressure. The next section we're going to talk about real quick is just what is temperature. And temperature has to do with, you know, gas particles, and these gas particles movement. So if I have a little gas particle here and a gas particle here and a gas particle here and a gas particle here, and we start to talk about their velocities, what we're going to do is we're going to have one go in that direction and one go in this direction, and we start talking about how fast these guys are traveling. If they're all the same gas particles, on average, the little arrows representing basically how fast they're going, their velocity, should be about equal. And so if we consider temperature at absolute zero, which is 0 Kelvin, at 0 Kelvin, there's absolutely no movement. These gas particles don't move at all. The more they move, the greater the temperature becomes. And so if we're at 70 degrees, we have quite a bit of movement. If we're at 0 degrees, we have no movement. And so the whole idea of temperature is the quantity of movement. So if we have these gas particles flying around the inside of, say, this circular container, as long as we have temperature, those gas particles are going to come up and they're going to collide with the surface of the container. And if they collide with the surface of the container, they're going to cause pressure. So we're going to start comparing some things. We're going to start looking at pressures as they relate, or I'm sorry, temperatures as they relate to pressure. And we're also going to look at if this container stays rigid, in other words, the volume stays rigid, how does that compare to temperature and pressure? Or if we allow volume to change, how does that compare? And so the next couple of laws that we're going to get into, or the next couple of things that we're going to consider, is what if one of these stays constant, either temperature or pressure or volume, what happens to the other two as they relate to gases? So in our next video, we're going to actually start to talk about what is going to happen if those things start to change. Okay?